I forgot to record. Yeah, so you obtain similar results, and you see that you do actually much better in these settings than other baselines, like for example, deep ensembles, which is like a very strong baseline in this setting. Deep ensembles would be this light blue curve. In MNIST, it doesn't do so well, and here it's slightly worse than our method. More things, you could see how things change as you reduce the size of your subnetwork. We use this 42,000 weights. The results are shown here with this triangle pointing down, which is the top curve in both plots. And as you reduce the size of your subnetwork, performance deteriorates. But you can still do quite well, even with subnetworks of up to only 3,000 weights. For example, you can still do better than the deep ensembles approach. Yeah.
You mentioned that one common approach is just like having the Bayesian layer on the last layer. So do you have like something which is related to what kind of subnetworks does your method discover? Like do you have some? Yeah,
like looking at what weights are important, and yeah, we didn't really look much into that, and it's hard to know because you will just add some weights from everything. The weights in the last layer are important. Yeah. So those are quite important.
I think like just simple thought, like for example, how many like fraction of weights were selected from each of the layers.
Yeah, that could be interesting. We didn't do that analysis. Yeah. Cool. So to conclude this, we have seen this subnetwork inference method. It can be easily applied to any pre-trained model. You just apply this technique choosing your subnetwork and then capturing uncertainty on those weights. It's more accurate than other approximations over all the weights, like factorized approximations and so on. It's scalable. You have this trade-off on your size of your subnetwork, but at least you will be able to apply it with a small subnetwork always. And it can outperform some of the best existing methods, like deep ensembles in these settings. We have seen that. Cool. Any questions on this? I'm going to move now to, yes. Sorry, can you repeat?
Is the code open source?
The code open source. I think so. Yeah, I think there is like a repo, and you can download this and use it. Yeah. Cool. So we are going to move now to a different topic. We are going to see now that if you want to do one of the things that is actually important when you implement these methods is to choose the prior hyperparameter, the prior variance. That's going to affect your, yes? Yes?
I was just wondering whether you have an idea about whether the Gaussian approximation in the subnetwork might be a better approximation of the Gaussian.
What do you mean, if it is better than for the full network?
Well, in the sense that in a larger neural network, the loss surface network is posterior, more kind of modem complicated.
Yeah.
So generally, that's the approximation for a small network.
Yeah. So there are some things there. What happens is that I mentioned this linearized Laplace, and actually what happens is that you do inference on a linear model, and in this linear model, the true posterior is never multimodal. You can show that the true posterior in the linear model is actually having a nice form. If you have like a likelihood function that is, you can show it in like typical likelihood functions like Gaussian or softmax, for example. That's going to give you a posterior that is going to be concave. And that's guaranteed that you won't have multiple modes. So I think that's why these Gaussian methods work quite well. Whether there is a difference from the full network or not, I think if you could put your Gaussian on all the weights, that's going to be always better. You won't do better by looking at the subnetwork. You will always have some deterioration in performance, but it's what you can do because of the scalability. You cannot really work with a whole set of weights. So now, just to move to the next topic, choosing the prior variance in your for making predictions with this approach is actually very important. If your prior variance is wrong, your uncertainties will be off. So you want to choose this quite well. And we're going to see now a method that will allow you to do that in modern neural networks, which are trained in a different way from how David Mackay was training neural networks in the past. And we're going to see that there is an important difference that actually makes David Mackay's approach break down when you apply it to modern neural networks. And we're going to see how to fix that. And again, this is some joint work with PhD students in my lab. Javier, David, James, Eric, Ricardo is a collaborator from UCL, and Eric Naisky, who was a postdoc in my group and now is faculty at Amsterdam. So what we have seen so far is that a Gaussian can be a poor approximation to the posterior of a neural network. But it is actually a very good approximation to the posterior of the linearized model. And that's why this linearized Laplace approximation works so well. And the reason for this is that this posterior in the linearized model is concave in most cases. So if your likelihood is softmax, Gaussian, you have this. So working in this setting is going to be quite good to use Gaussians. Now, one of the things that I have mentioned is that choosing the prior variance is very important. And it's going to determine the quality of your error bars. The question is, how did you tune this prior variance in the previous work, in the subnetwork inference work? Actually, we didn't use David Mackay's approach to choose hyperparameters. We used cross-validation. Why we didn't optimize this approximation to the model evidence? The reason is it didn't work in our case. And you wonder why it's not working. David Mackay has amazing results showing that it works really well. And in our case, the prior overestimated uncertainty. And you can see it here in this example. This is the predictions that you would obtain with different values of the prior precision. So a smaller prior precision means more uncertainty, higher prior precision, less uncertainty. And here you have too few, the uncertainty is too low, the uncertainty increases. This is what the model evidence would tell you to choose. But this is slightly too large. In this central region, even the uncertainties are way larger than the range of variation of the data. And this is slightly too large. Actually, something more reasonable would be some value like this. But the model evidence approximation was not working. It was choosing this other value. And this was creating a lot of frustration with my students. They were trying to apply this method that David Mackay was doing, and it was not working. And the only option was to choose this parameter by cross-validation. So the question is, why is this not working now? And David Mackay didn't have these problems. There is a very good reason for this. So David Mackay, he was training his networks using second-order optimizers, batch second-order optimizers. These optimizers, they are very good finding local minima of your solution. And they will find some solution where the gradients of this log posterior in the neural network are almost zero. They are very good at optimizing. And you can show that if the gradients of the log posterior in your original neural network are zero, the gradients in the posterior for the linearized model are also zero. You can show that very easily because basically the gradients of the two models are the same, because the linearized model is just using the gradient, it's a linear model with the gradients of the original model. So David Mackay was finding solutions where the map solution for the weights of the neural network was the same as the map solution in the linearized model. And this means that if you look at the approximation of the model evidence for the neural network and for the linearized model, the two have exactly the same formula. And when David Mackay was choosing optimal prior hyperparameters, these optimal prior hyperparameters were also the optimal prior hyperparameters for the linearized model. What happens now? We are no longer using second-order batch optimizers. We are using a stochastic optimization. We are using early stopping. We are using a lot of techniques that actually don't give you a solution where these gradients are actually zero. And this means that the model evidence in the linearized model and the model evidence when you apply this Laplace approximation for the neural network are different, and there is this mismatch between what it was done before and what it is being done now. So what we are going to propose here is to say, forget about the model evidence in the original neural network. Let's optimize the evidence, the model evidence, for the linearized model. We are going to apply now the Laplace approximation in the linearized model, and you are going to do hyperparameter tuning in that setting. The most important thing is that now the posterior mean that, or the point estimate that we found for the neural network is different from the posterior mean in your, sorry, not the posterior mean, the map solution. The point estimate that we obtained training the neural network is different from the map solution for the weights in the linearized model. And now, if we want to apply the linearized Laplace approximation in your linearized model, the first thing you need to do is to find the map solution in your linearized model. This is a unique solution in this case. With the Gaussian likelihoods of softmax, we mentioned that the posterior is concave, so there is only a single maximizer, and we can find that. Once we have found that, then we just apply the Laplace approximation to the model evidence on this linearized model. It's the same as before with one difference. Now here we have the predictions of the linearized model evaluated at the map of the linearized model, not at the point estimates of the weights in the network. And now here we have also the map of the linearized model and not the point estimate of the neural network. You can apply the same thing as before. You can obtain the generalized Gauss-Newton approximation to the Hessian. It's the same as before, but now these G matrices are evaluated at the map solution for the linearized model and not at the point estimate for the neural network weights. So that's kind of the key idea that we are going to follow. You train your neural network, you find some point estimates of the weights, you linearize your neural network, and you obtain a corresponding linear model. And now you are going to apply the Laplace approximation on this linear model. For that, you need to find now the map solution for your linear model, and then you just apply the standard approximation for the of the model evidence for that linearized model. Are there any questions so far on this? It's clear? Cool. So if we want to put this in practice, there is one thing that we need, and it's precisely this. We need the map solution for the linearized model. And that is a model that is built on these Jacobian features. So it's not straightforward how to do this in an efficient way. But you can actually find this map solution in the linearized model very efficiently. The key thing is how to obtain gradients. You just need to do gradient-based optimization. How do you find the gradients of that? And you can actually do it very efficiently. The key thing is to compute this dot product between the Jacobian features. These are the features of the linear model, and some weight values for the linear model. No, you just need to do this. And then there are some other things here, but maybe the most important part is this. You can actually do this very efficiently using either finite differences or forward differentiation to approximate this Jacobian vector product. This is just a Jacobian vector product. There are efficient ways to do this. And it turns out you can actually efficiently compute the gradients on this linearized model with very little computational cost. Like, for example, 2 forward passes and 1 backward pass in the original network. So this is very little overhead from what it takes to optimize the original neural network. So you can do it very easily. I won't go into the details of the algorithm, but it's there, and you can find it also on the papers if you're interested. So we can now find the map solution for this linearized model very easily. And you can see how it works when you tune hyperparameters in that setting. Now it works fine. You don't have this problem of overestimating the uncertainty as before. Before you had like too much uncertainty here. Now you obtain much accurate results. I won't go much into the details. There is one thing that we are not doing here. So here, these G matrices that appear in the generalized Gaussian approximation, they depend on the predictions of the linearized model at the map solution. And this means that you will have to recompute all these matrices every time you change your prior hyperparameters. The prior hyperparameters are going to change the posterior mean of the linear model. This W prime is going to change, and then you have to change this. It turns out these G matrices, they don't really change much because the predictions of the linearized model are actually quite close to the predictions of the original network. So you could actually just compute these matrices G using the original outputs of the neural network, and that's actually fine. And I mean, we show here that on the left and on the right, you use either WMAP or W tilde to compute these matrices, and it's more or less the same. So what makes a difference is to tune the hyperparameters using the evidence of the linearized model or the evidence of the original neural network. And the evidence of the linearized model works much better. It turns out that we mentioned this thing that you don't end up in a solution where I mean, you don't end up in a solution that it's a local minima for the original neural network because you use a stochastic optimization and other things. It turns out that modern neural networks, they're also trained with things that David Mackay was not using, like, for example, batch normalization. Batch normalization helps you converge faster, and it improves learning in many settings, so people use it quite a lot. It turns out that there are some conflicts between batch normalization and this linearized Laplace approach, because with batch normalization, the output of your network is insensitive to the scale of your weights. So if you scale your weights, then by a constant, you're applying batch normalization to a layer, and you make the weights in this layer, you multiply them by a constant, the output of your network actually doesn't change. And this is not really captured by the linearized Laplace approximation. In particular, what is going to happen is that the output of your network doesn't change, but if you look at the Jacobians that you obtain, those Jacobians are sensitive to the scaling. I won't go much into the details of that, but if you scale the weights in a neural network with batch normalization and you just scale the weights in a layer by a constant, the output of the network is the same, but if you look at the Jacobians are scaled by this constant. And this means that if you have different layers in your network with different scaling constants, then your Jacobian features are going to change and have different magnitudes across layers. This means that if you use a single prior variance shared across all the layers, you are going to run into problems, because you will have now arbitrary scaling constants in your features in your model, and that's going to affect the scale of your weights as well. Fortunately, what you can do is just have one scale or one prior variance parameter for each different group of normalized weights. So if you have several layers with batchnom, you just put a different prior on each of these layers, and that's going to adjust your prior to the scale of your features and the scale of the weights for that network. And what you find is that when you scale the weights by different constants and you tune your prior hyperparameters with different weights per layer, then the uncertainties don't change, which is actually good, and that's going to improve performance. So just to look at some results, we can see the results with our proposed approach to tune hyperparameters, where you use this model evidence approximation for the linearized model, and where you use layer-wise prior hyperparameters. And you see that in general, you perform better across many different architectures. There is this one where we don't perform better, but it's slightly very close to the other approach, where you just have a single parameter shared across all layers. And this is an approach that is different from this batch normalization. FixUp is doing something different. But the message here is, if you tune hyperparameters using the linearized model, which is the top row in the column, in the table, that's much better. And usually layer-wise alphas is usually also better. These are for networks with 46,000 parameters. Again, it's the largest we could work with. But you could use this also with the Kronecker product approximations. And it does more or less similarly. We do it here with networks with 23 million weights using these Kronecker product approximations, and you find that using this linearized model evidence for tuning hyperparameters works better. One last thing also. You may wonder, we have this linearized model which has the output of the network, the gradient features, but maybe we can actually simplify this. Maybe we don't really need to model deviations from the original output of the network. It turns out that if your last layer is linear, this linearized model, the features already have as entries the activations of your last layer. If you think about a neural network with a linear last layer, the gradient of the output of the network with respect to the weights in the last layer is actually the activations of the last layer. And if you have a linear model on top of those activations, that's as flexible as the original neural network. No? So the linearized model is actually extremely flexible. It's as flexible and powerful in terms of modeling as the original neural network, because some of the features in your Jacobians are going to be the activations of the last layer in your network. And then you could think of saying, let's try to work with this model instead of the original one. The uncertainties are going to be the same, but now what happens is that this other model is not really describing the errors of the original network. No, this model is just the weights W are going to compensate for any potential errors that the original network makes, no, because you are just modeling deviations from the output of the original network. And this means that when you find the map solution on this model, it's going to be harder because you're just trying to find a value of W that compensates for the errors in this model. You could just work with this other model, and finding the map solution is going to be easier because you just try to describe the data directly with the model, and you don't try to describe the errors of another model. Anyway, I won't go much into the details of that, but what happens is that if you choose prior hyperparameters with this simplified model, you obtain better results because finding the posterior mean is easier in that model. And you see that you do much better using the simplified linear model and then using these layer-wise prior parameters. Cool. So this completes this part here. We have seen that there are pitfalls in the application of the linearized Laplace approximation to modern neural networks. In particular, because your neural network is not going to be fully optimized, and then the point estimate of the weights that you obtain for your neural network is not the same as the point estimates that you would obtain for the linearized model. So training easily doesn't find a posterior mode in neural networks at the moment. With modern neural networks, you can still linearize the network around your point estimate. You can then obtain accurate uncertainties by tuning prior variances using the model evidence of the linearized model. And we have shown that there is an efficient algorithm for finding this map solution in the linearized model. Normalization layers also introduce problems. They introduce invariance in outputs, but the uncertainty is not invariance to scaling of the weights. But you can solve that by using different prior variances per normalization group. And finally, you can use this simplified linear model to estimate better the map solution in the linear model and to do better tuning of hyperparameters. Cool. Any questions on this? No? Just one?
Yeah, maybe you see, like you said, that you can't last on the initial value for the variance of the normal distribution for the prior?
The prior, yes.
Do you see any relation to the posterior effect?
Can you repeat?
Do you see any relations to the posterior effect?
Yeah, so this is very different. So with the cold posterior effect, the idea is that if you do inference on a neural network, typically you obtain worse results than finding point estimates by stochastic gradient optimization. And actually, if you do inference on this neural network when you try to I think you increase the weight of the likelihood or so, you try to make the likelihood more peaked, and then you focus more on the data, things improve. Here what we find in our experience is that usually using these uncertainties improves by default. So if you take your point estimates of your neural network and you make predictions with those, you will get some log likelihood values. If you consider the uncertainties that come from this linearized Laplace approximation method, you get even better results. So we don't observe any of this called posterior thing in this setting. My intuition of why this happens, doing Bayesian inference on the linearized model is very easy. The posterior is concave. You don't have crazy multimodal things. And it could be that doing inference on neural networks where you don't use this linearized approach is more complicated, and maybe your inference is not so good, and maybe that's why you have this cold posterior effect. And I think it's a phenomenon that is not super well understood, this cold posterior. There are many papers claiming it originates for different reasons. But here we don't see that effect. Cool, another question?
You mentioned that we cannot replicate David Mackay's results because we switched optimizers. Are you saying maybe we should go back to second order optimizers?
No. No, because first of all, those were like batch optimizers. You won't be able to do that on very large data sets. They're also not scalable, so they use also, the cost of those methods is quadratic in the number of weights. So you won't be able to use those. And what people have found in practice is that also optimizing these networks a lot is not so good, because you could overfit. And second order optimizers may have those problems. I mentioned that you could use the Kronecker factor approximations to do optimization as well, no? Because they are estimating the curvature. It's the same, they are approximating the Hessian, and they are estimating the curvature. You could then use those methods for optimization, and in some cases they can also produce overfitting. I think the reason is that the stochastic optimization usually is very good to find solutions where the network generalizes well, and with other type of optimizers, maybe things won't happen. So I don't know, I think there are many people working on second order optimizers. I actually have PhD students working on that. So I don't think it's a bad idea. I think there are still potential things to do there, but it's going to be challenging. Cool. Any more questions? Or yeah, one more. Sorry? Post-optimization. What is a post-optimization? With the subnetwork inference, yeah, that's right. So you train your model in any way you want, and after you have trained the model, you select which weights you are going to consider uncertainty on. Cool. Good. So we are going to see now an application of these methods to image reconstruction, in particular to X-ray image reconstruction. And this is also a collaboration with Javier Antoran, who is doing a PhD with me. Ricardo Balbano is a collaborator at UCL, and Johannes and Bangti are also at UCL. So the problem here is to do inverse imaging. We are going to have an object that we want to scan. We want to get like a cross section of this object with X-rays. This is a walnut, and we're going to get a section. This walnut is like a commonly used in this area, because you can scan the walnut for a very long time with X-rays, and no one is going to worry about that. You cannot do that with a person. So you can expose your walnut to a lot of X-rays, and there is no problem. So you are going to have some X-ray source. It's going to go through the object, and you have some detector cells. And this is going to turn around, and you will get many of these measurements. And now, what is going to happen is that the object is going to change the X-rays in different ways as they go through the object with this angle. And you can represent this just with a simple linear operator. So you have you can imagine that you have your original image that represents the visualization of the object, you have this matrix A that represents how it is scanned with the X-rays, and you're going to have some measurements Y. This is what you observe in practice. Why? You know the way the X-rays generate Y as a function of the original image by this matrix A, and then you have obviously some noise in your measurements. So this is just a simple regression problem where you just have some feature vector X that represents your image. You don't observe X directly, but you can measure it by projecting it on the rows of this matrix A, and you get some measurements. And this would be representing, for example, the measurements Y, and this is the value of X that you would recover after your scan, which is this section of the walnut. These things here on the corners are just zoomed parts of the image. That is just you see it in higher detail. So typically what happens is that the number of measurements that you need to reconstruct the image is actually much smaller than the dimension of the image. And the reason for this is that the images are smooth. There is not a lot of crazy variations in the medical images. So you can actually reconstruct these images using a relatively small number of measurements. This means that the problem is actually underdetermined. If you want to, typically you will have less observations in this regression problem than unknown variables. And you need to introduce regularization to solve this problem. There is actually a state-of-the-art method to solve the problem, and it involves neural networks. It's something called the deep image prior, and it's actually extremely surprising. When I got to know about this, I was very surprised. So what you are going to do is, instead of finding point estimates of the image on its own, what you are going to have is a deep neural network called a UNet. Michaela talked about this also in the summer school. The UNet is going to have some weights and some input. And what you are going to do is now fix the input to some value. It could be anything. And now you are going to optimize the weights of your neural network instead of the image directly. And that's going to introduce some constraints in the type of images that you would be obtaining. You cannot really get now crazy images. You are going to get only smooth images because of the way this network is done, no? Because it does some dimensionality reduction of the input, and then it does some dimensionality expansion. And because of this, you are going to have smooth images. That's why this is called the deep image prior, because you enforce into your image the regularities given by this neural network. You also have another regularizer here, which is called the total variation, that enforces a smoothness between the image values. So you obtain the output of the network is your image, and then you penalize the absolute value of the differences between nearby pixels. And that's going to introduce some smoothness as well. Now, this is a state-of-the-art method to reconstruct medical images. The question is, can we get uncertainties in our image reconstruction using the linearized Laplace method? The image is just the output of the neural network. Linearized Laplace is a state-of-the-art method for getting uncertainties on the output of neural networks. So we could apply it in this setting. It's not straightforward. The first thing is that the total variation, you could think that the total variation could represent a prior in output space. The problem is that the linearized Laplace needs Gaussian priors. You are working with the Hessian. The Hessian represents second derivatives, and this thing doesn't have second derivatives. The second derivatives of this are just 0 because of the absolute values. So we are going to now find a Gaussian prior that has a similar effect as the total variation. And you have here the samples from a total variation prior. It's just obtained by taking the exponential of the total variation metric times a constant. And we have a Gaussian prior on the weights of our neural network. And this Gaussian prior is going to introduce correlation between the weights. When we sample the weights of our neural network with this Gaussian prior that introduces correlations between weights that are close to each other in a filter, we get this type of samples that are very close to the total variation prior. I won't go much into the details of this, but the idea is that we just have a prior on the weights of the neural network with some length scale parameters that represent the amount of correlations and some amplitude. And we are going to optimize this using the approximation of the model evidence from the linearized Laplace method. So let's how, I mean, the method is in the end similar to what we have seen before. Let's see what it is. So you're going to train now your U-net with the total variation regularizer, minimizing the reconstruction error. And you could do this in any way. You get a point estimate for the weights of your network, and you get a point estimate for the reconstruction of the image. You are going to linearize then the U-net around the selected weights. You build your Bayesian linear model using the features that come from the Jacobians of this U-net. You can then optimize prior hyperparameters, maximizing the model evidence for that linearized model. The model evidence in this case is exact because the likelihood is Gaussian in this case. So we don't have to do like Laplace or anything. This is exact. And then we are going to make predictions with the original U-net. I mean, we get the point estimate for the image from the original U-net, but now we get the uncertainties from the Bayesian model. There are more things described in the paper on how to scale this. We need to do some approximations to scale these computations, but you can still do it. And you can look at how this works. So I have highlighted here some. This is the original image of the walnut with some regions that they are zoomed in to get more detail. And this is the reconstruction from the deep image prior, which is quite accurate. It's more blurry in this region, but it's still quite good. You can look at the errors, which are shown here. In this corner here, you have higher errors when you compare this one and the ground truth here. No, the errors are more in this corner. And you can look at the uncertainties given by the linearized Laplace method. And you see that the uncertainties are actually higher in this region, which is where the errors are also high. You can compare with a baseline, a simple baseline, which is what we are using in this setting, which is just Monte Carlo dropout on your U-net. And you can see that Monte Carlo dropout also reduces a bit the performance of the reconstruction because you are training your neural network with some randomness and you are not finding point estimates. So the reconstruction is slightly worse. The signal to noise ratio instead of 26 is 23, slightly worse. And the uncertainties are way worse than what we get. You look at the errors of dropout, and again, they are quite high in this region, but it's saying high uncertainty in all these regions. And the test log likelihood is worse in this case. We get higher log likelihood. Good, so this more or less, I'm going to skip this in the interest of time. So this concludes this part. We have proposed a method that uses this linearized Laplace to obtain a probabilistic formulation of this deep image prior. It's based on Gaussian priors that have a similar effect on this total, as this total variation regularizer. It produces well-calibrated uncertainties. We have seen that we improve over baselines such as Monte Carlo dropout in this case. Yeah, and then this works really well in this setting. Yeah, I don't know if you have any questions on this part. Yes?
I have a question about your truth. So the thing you're using on the top left is the truth.
Yeah. Yeah.
Isn't it likely that that isn't the exact truth? I mean, isn't that the point of the...
Yeah, the question is what is the truth? I mean, this has been reconstructed. So the way this works is that you reconstruct this with a lot of data. That's why you have this walnut that you can get out of measurements of the walnut, and that's and the idea is to try to reconstruct this with less data, with less observations. Right. Cool. Yeah, I don't know if there are any other questions on this part. I can tell you a bit about the stuff that we are thinking to do now. We saw this talk by Tom on ways to collect data efficiently using information theoretic metrics. You can actually do the same in this setting. You can use your uncertainties from your predictive model to decide what measurements to do next. And And it's actually very easy, and you can just get uncertainties from your predictive model, and then you could look at what measurement you could do next, so that you improve your reconstruction by just reducing uncertainty. And that's a way to accelerate this process of scanning things. Obviously, there is some computational cost attached to this, but if you could imagine that you can solve these problems fast, you could speed up the scanning process. And this could have applications in many medical imaging settings. You could imagine people that go to MRI machines and they have to be there for quite some time. If you can accelerate that, that could be also quite good in practice. And you could think of using this type of techniques. Obviously, these are experimental methods, and they are not really directly able to, you won't be able to translate them directly to these machines because the computational cost that is involved in them. But I think there are many interesting opportunities here for things in the future, no? Where you could think of these methods actually being implemented in real world machines. Cool. So I think that concludes the presentation, and I think we can have a break now, and then we will come back with Cecily, and yeah, see you soon. Good.